Okay, so now we know that it's anticlockwise. So the next thing we do is just to plug in the formula. So now we have tangent pi is equal to IZZ over IYY tangent theta. So this expression will be equal to, so IZZ is 21.4, IYY is 6.74, and then you have tangent, and you have to insert your minus 45 degrees. Okay. So you have tangent of minus 45 times by 21.4 divided by 6.74. Okay, then I'm going to immediately calculate pi. So inverse tangent is equal to minus 72.5. Okay, minus 72.5 degrees. Okay, so minus 72.5 degrees means the neutral axis is going to rotate in a counterclockwise direction. Okay, so now where is this 72.5 degrees? Okay, so I'm going to draw the actual position of the neutral axis. Okay, so 72.5. Okay. So this is the orientation. So this is the position of the neutral axis. .5 is measured in this direction. Yeah, undo. Okay, so this is equal to 72.5 degrees. Okay, that is the orientation. Now, usually this sort of question were asked, okay, what were, or if you look at the homework, they were asked, what is the orientation, okay, orientation of the neutral axis from the horizontal axis. Okay, so from the horizontal axis is not 72.5. So let me sketch out where the orientation of the horizontal axis. So this is known as the horizontal axis. Sorry. So this is known as the horizontal axis. Okay, so I'm going to say that this is your horizontal axis. Then if it's horizontal axis, now we want to find this value. Okay, so we are going to find this value. Right, so from the horizontal axis is equal to 72.5 minus by 45, because this is the 45 down here, and this is, we know that this is your 45, the theta is 45, so it's equal to 72.5 minus by 45, 27.5. Okay, and then you have to put in anti-clockwise rotation from the horizontal axis. Okay, so that is how you determine the orientation of the neutral axis for centric, unsymmetrical, bending. Okay, so again, the most important thing over here, remember that the transformation is attached or will rotate with the structure. Okay, why? So that it's easier to determine your IYY and IZZ, number one. And then the next thing that you have to remember is all the rotation is from the Z-axis, okay? And or relative to the Z-axis, clockwise is positive, anti-clockwise is negative. Most important diagram is this diagram over here. Are we clear? Any questions so far from anyone? This is I think this is I think what this topic is important is it's important to know how the formulas has been derived, and you have to follow the orientation originate from the derivation, how everything has been derived. So this diagram is really, really important. You mess it up, or if you don't remember, it gets really, really confusing. Okay? Any questions from anyone? Okay, I don't see any questions. So the next one, again, is going to be a very quick revision. It's a different type of bending, and this the type of bending that we are going to look at, and this is important. Later on, we're going to apply the same concept in week 9 and week 10. Okay, so we are going to look at eccentric. We're going to start with symmetrical. Okay, bending. And we did mention this before. Okay, we did mention this before, and I'll help you recall later on. Okay, so now I need you all to get this diagram. It's on Avenue to Learn on week 2 lecture. I think I did post it on Avenue to Learn that these are the examples of figures that we're going to use. Okay. Right. So this is a structure that's under eccentric symmetrical bending. Okay. So the thing to focus on is at uh point or at this point over here, okay, or at this region over here. This is where failure will occur. Okay, if this structure is loaded, as you can see, the horizontal load is at point A, and at point B you have two forces that's pulling it out. Right, failure will occur at point C or along the axis that go through point C. So I'm going to write out the formula for centric and eccentric. Okay, so let's look at centric. Symmetrical, bending, and this is easy. You guys have seen this, and this area easy. So stress X is equal to minus m z over IZZ multiplied by y, or stress X is equal to my over Iyy multiplied by z, or, okay, not n, okay, because it's symmetrical. Usually when it's symmetrical bending, moment can only be applied on one axis only. Okay, if it's gone through two axes, we know the problem. If it's gone through two axes, then it becomes what? Unsymmetrical. Okay, then it becomes unsymmetrical, which we are not able to do. Okay, then if we look at eccentric, symmetrical, bending, right? So what we have now is stress X is equal to Px over A minus, okay, Mz over Izz multiplied by Y. Okay. It is eccentric is because this structure is under both axial loading and is also under loading due to bending moment. Okay, also due to bending moment. So this is the case. On the left hand side, the figure shows uh, 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 the structure that's under eccentric symmetrical bending. Okay. Now you guys will understand what do we mean by symmetrical. The stress field on the on alpha, beta, I, and J, like what I explained to you last week, are equal. Okay. So for this case, you can see that where failure will occur at point C, right? You have a force P at point A, and at point C, you have a reaction F. Okay, I do apologize. Let me put this as F. Okay. And then due to the distance, okay, so now if we look at the moment, right? Moment in Z is equal to P prime multiplied by D. That's the moment now. Okay. So if we were to visualize how this structure will deform due to bending moment, it will fail in this orientation. So I'm going to sketch the failure orientation. So it will look like this. Or how it's going to bend. It's going to bend like this. Okay. So that is why if you look over here, you have a counter moment acting this way, because on the left hand side, you have a moment acting that way. You have the other moment in the Z direction also. Now, the transform, once you got the moment transformation, whatever I teach you is still the same. Okay, so at the head of the moment vector will be under compression. The tail end will be under what? Will be under tensor. Still the same. Right? So whatever I taught you before applying the moment vector of the head is compression tension. It worked for centric symmetrical loading, centric unsymmetrical loading, and it also works for eccentric symmetrical, eccentric unsymmetrical loading. That principle always work. Okay. So now, how does the stress field work now? Okay, and I did sketch how the stress field will behave, and I think this was done in. Wait, I have to look. Probably in last week, not hold on. Probably we did last week. Let me check. Yep, this is the stress field on how. So this is on week 1 Thursday. Okay, so I'll copy the whole diagram again. Okay, I'll copy the whole diagram again. So we have drawn this. I'm not going to go through drawing all this again. Okay. So this is how the stress field will look like. Okay. The only difference is I have to, if I